In this next recording, we're going to modify base case example 8, and the goal will be to size the tank so that it stays within 10-meter elevation variation for a demand pattern that starts at 1, has a multiplier of 3 at 1800 hours, and goes back to 1 on a repeating cycle, mostly because those are easy to enter. And so our first step will be to convert the problem into SI units, because I'm pretty sure it starts out in US customary. So let's go ahead and...
No, you are increasing here by $3 something, the cost. Here, they're doing the demand pattern. We have used the factor of 3.
Right. Because everybody comes home at 1800 hours, takes a shower, and uses the water closet, so the water demand goes up.
Yeah.
Okay, I've got 51 minutes of program time available, so we should be good in this case. So let's start the program. I'm going to open up example 8. So here's example 8, and let's take a look at the pipe dimensions. It looks like it's currently in feet. So 6,000 feet is about 2,000 meters. I'm going to switch to meters.
Yeah.
10 inches is going to be 250 millimeters. Wait, is that right? 25 cents, yeah. Should be about right. Roughness, I think we'll leave it be for the time being.
Constant.
Next pipe. Actually, I think I'm being an idiot. Let me reopen the file. We'll stick in US customary because I don't want to waste a lot of time changing things and break something.
So the unit will be the same. Have you changed the units? No.
Not yet. Okay, that's a good start. Ah, shit. I thought I had the example already in SI units. Looks like I don't. Alright, that's a shame. Ooh, and I lost my connection.
The server.
Okay, returning to our example, here's our tank, and you'll see this section volume curve. There's nothing there, so all the tank information is contained in these few lines. So it's a cylindrical tank with a 50-foot diameter. The lowest level the tank can reach is 0. The highest is 150, so this is actually a very tall cylinder. It's starting out at 135. The base elevation is 180. So 180 plus 135 gives you 315 is the starting head. So if we were to draw that tank, it would look like this. Here's what is modeled in the computer. A cylindrical tank. That's supposed to be a cylinder.
Diameter is at 50, I guess. No.
Base elevation is 180. The maximum level 150. That's a very tall cylinder. And the diameter, like you said, was 50 feet. And this one looks like it's starting out with the water at 135 feet. So the total head, at least at the starting condition, is 135 plus 180, which is 315. If the network needs water from the tank, it's going to come in initially at this head, and then the tank water level will drop. And so then the head will be reduced, it'll drop some more, and the head will be reduced, and so on. And the computer program will track that once we turn on the extended period simulation. Here's our pump, and it uses pump curve 1, so let's take a look at the pump curve. So our pump curve, different location. Looks like shutoff is 200, and that's a huge 2,000 feet per second. It's around 100. So there's our pump curve. These are fairly large numbers for a pump, so I suspect that's not a single pump. That would have to be a lift station, combination of multiple pumps. And let's look at the supply reservoir. The supply reservoir has elevation 155. The first node in has elevation 0, so that's gravity flow. That's probably a mistake. That node has 155. Let me fix this because that can't be 0. It makes no sense. So the top of the water in this reservoir is at the same elevation as the first node. So there's no natural way for the water to go into that network. We need the pump to force it into the network. Then at each node we have base demands. So we have non-zero demands everywhere. So we expect if this reservoir elevation is maintained at 315, that is enough for gravity flow. The pump won't run very much. Let's go ahead and run the simulation. and it has a single period simulation. And if we look at the pump is contributing 19 cubic feet per second, and it's actually putting water into the storage tank. Now let's disconnect the pump. The easiest way to do that is to change this from open to closed. So now everything to the left is no longer part of the network. It's gone. What do you expect the flow in that pipe to do?
Like this is how much it at elevation, how much head it is from the top to the node.
And right now it's claiming that the flow goes from the network into the tank.
Mm-hmm.
Remember, we have a pump removed. So now it can't do that. So the only source of water has to be from the tank to the network. This arrow should change direction.
Yeah.
Sure enough, I mean, it does. No surprise there. Now let's see if there's actually any demand curves laying around in here. That's a pump curve, demand pattern. This has no demand pattern, so we're going to have to create one. And the one we wanted to create is we want to go out here to 1800 hours. I wanted to make that a multiplier of 3. 18, 19, 20, 21, 22, 23, 24. So 6 increments. I want to lose 2, so this is trying to do this in my head. Okay, so we've handled the last 6 hours, and now we want to go ahead and I want to do the same thing for the first 18 hours. So half of 18 is 9. So at 9 hours, I want to have a multiplier of 2. At time 0, I want a multiplier of 1. See if I can pull this off in my head. 0.2. Data entry's not being. That's. Let me just do it the right, easy way. Nine minus 1.125. So I'm trying to get linear variation without thinking about that. It'd be 125 twice is 25. The other 25. 1.375. And that should be 1.5. Okay. 1.625. .75. .875. Almost done. So 2.125, 2.25, 2.375, 2.5, 2.625, 2.75, 2.875, 3, 0.6, 2.3, 2.0, 1.6, 1.3, 1, there we go. There's our pattern. It's not perfect, but that's what I was trying to achieve. Ramp up, ramp down.
So what values you have kept in the decimal you are multiplying?
1 up to 3, back down to 1.
With the step size of?
Peak is around the 16-hour block. I wanted it at the 18-hour block, but I don't want to go rearranging things. It's showing that our average rate is 2, so the average is essentially the area under this object. Okay, so do you understand how to put the data in?
You have used different decimal points, multiples of points. So,
right.
So how did you take this? Like how did you add the multiple points? Or the step size of like you were stepping?
I just entered them, so you just highlight the block that you're interested in, enter it, and it adjusts it.
Yeah.
So 326. So that's how I got it. I was trying to get it to ramp up and ramp down, and I'm off by 2 time blocks. I'm not going to mess with it.
Okay.
If we really cared, we could take 3/10 of that one and make that 0.7, and it'll look prettier. Okay, so I will keep this. That's my demand pattern. Let me turn on my pump again.
No.
If I rerun it, there's no change because we haven't changed the time. The way we know that is it says we did a single period. So now in the data block, do you remember what we have to change to activate that demand pattern?
Like we have made the pump 0.
Options times. You change that from 1 to 24. Let's do 24 hours initially. The other thing we have to do is we actually have to assign the demand pattern to all the nodes. The easiest way to do that is group editing. Demand pattern on junctions, I'll put a 1 there. That should go to my pattern model. Press the okie dokie button. Now when I run it, this will no longer be single period, it'll have the 24-hour block. Except we got our first warning message, which is negative pressure at hour 11. Let's go watch what's going on. Let's change these from those to pressure. And it'll go dark blue before it goes negative. So the problem I see is that the tank is draining. And here's, this one's about to go negative. There, it went negative right there. So let's go take a look at the tank water level. Okay, we know that if it gets below 180, the tank is dry. Right here, it's getting below 180. So we either need more volume in the tank or we need to make the tank taller. Let's go for more volume because that's easy. How do we make the tank have a bigger volume? Change the diameter.
100 or 150.
Let's go to 100, which should be 4 times the volume. Choose save. I'll leave this up because I don't actually need to change that. Let's rerun the simulation. Well, we got to 180, we got to 260. Yeah, it's this right edge of the network. At this point, volume alone isn't the question. We probably need to let the tank be taller, so we'll change it to 200. And we'll actually start with it full. And this is what I would say is the trial error process of getting a conceptual design. Run the simulator, still get the error message. Oh, at least we got an extra hour. Yeah, I can almost get it to 24 by making these pipes bigger. So at this point, we're doing strictly hydraulics. Successful run. So by making this pipe, and that pipe bigger, and I made the tank considerably bigger and considerably taller, we were able to and we still get pressures below 25, but we don't go negative. And if we look at the tank head, which is proportional to the tank drains, and starts to fill. So let's see if we can run this for more than 24 hours. How do we run it for more than 24?
We increase the time.
And how do we enter that information?
Hours, where is that?
Options,
Yeah, hours.
times.
Time, yeah. This will be 40.
Try 48.
Like logically, you switched off the pump.
No, the pump is now on.
No, just in that case, whenever you're increasing the diameter and the height, and then again you are increasing the pipes.
There's the pump performance right there.
Yeah. Like this one is blinking, means
it's highlighted by the marker.
Ah.
Let's go take a look at the tank real quickly. Yeah, we're still not quite getting the tank to refill. Maybe what we need is a better pump. Easiest way to do that is to increase the speed to about 1.5. I think that should really crank up the flow rate. Now that's a hydraulic modeling hack. You actually would want to go to a different pump, but let's see what happens if we do that. Yeah, there we go. Good clean run. Time series, I don't want pressure, I want head. In that case, the tank didn't drain, so the pump was doing more than we would expect. Yeah, the pressure's all pretty high. So running the pump at 1.5, the design speed is probably more than necessary. Let's go to 1.25. Because we want the tank to actually drain and fill, otherwise there's no point in having a tank in the system. Okay, that's better. That is pretty much extended period simulation in a nutshell.
Yeah.
We used it as a way to guide some design decisions on tank size and pump performance. Now in this particular example, the numbers we chose are ridiculous. You probably wouldn't run a pump at 1.25 times its design speed unless you wanted to break it. And you probably wouldn't have a tank that's 100 feet in diameter and almost 200 feet tall sitting on the ground. That would be very hard to build. Okay, let me exit. Actually, let me save this as ECTS EX8. I want to call this playground or something.
STC 223, 2023.
And what were we doing? We were playing What If. There, now the work is saved. I'll exit and I'll turn off the recorder and then we'll move on to the next topic. Okay, do that. Stop